Hello everyone, in this video we will learn all about antiderivatives. To begin, find the derivative of the given. If you are given y is equal to 4x cubed plus 5x squared plus 6, now take note to find its derivative, multiply the exponent and the base and minus the exponent by 1. So given this one, its derivative would be 12x squared, derivative of 5x squared would be 10x, and derivative of 6 is 0. Now, to find the antiderivative is basically to reverse the process. Now, given the same equation, so if we're given 12x squared plus 10x, we will get its antiderivative. Now, take note, when we solve for derivative, we multiply then minus 1. So for antiderivative, we will plus 1, the exponent, and divide the new exponent from the given coefficient. So given this, so we have 2, so plus 1. So 2 plus 1, divide that from the given coefficients. Then for 10x, we have the exponent of 1, so plus 1, so divide this by 1 plus 1. Then we will always have this plus c, so meaning it represents any possible constant. So simplifying, we will get this. So 12x cubed divided by 3, so 4x cubed. 10x squared divided by 2 is 5x squared. Then plus c, in which it is basically the original given. So the c here represents any possible constant. It's because if I will give 12 here, still the derivative here still 0. So take note, antidifferentiation is the process of finding the antiderivative. The other term for this is integration. It is the process of finding the integral. Now, in symbols, we will write it this way. So this is the elongated s is the integral sign. 12x squared plus 10x is the integrand. And dx here will always go together with the integral sign. 4x cubed plus 5x squared plus c, which is the antiderivative of the given, is basically termed as the general antiderivative. While c here, it is considered as the arbitrary constant. Now, let's have this. These are the basic integration rules, or they are the basic antiderivatives of algebraic equation. So take note of the rule. Add the exponent by 1 and divide the given with the new exponent. So, for example, find the integral of x cubed dx. So it will become x to the power of 4 over 4, then plus c. Another example, if we're given find the antiderivative of 3 dx, so take note it is a constant, so therefore its antiderivative would be 3x plus c. Another, if we're given find the antiderivative of 8y dy, so take note the exponent of y here is 1, so that would become 8y squared over 2 plus c. So since we can still simplify, so final answer is 4y squared plus c. Another, find the antiderivative of dz. So take note here, nothing is written, so the default here is actually 1. So with this, our answer would be z plus c. Another example, find the antiderivative of x to the power of 4 plus 6 dx. So take note, x to the power of 4, so plus 1, so x5 over 5. If we're given here 6, so that would be 6x, then plus c. Okay, another. If we're given 4x to the power of negative 3 dx, so take note, our exponent here is negative 3. So negative 3 plus 1, so that would become x to the power of negative 2 over negative 2 plus c. Or simplifying further, this would become negative 4 by negative 2, so negative 2x to the power of negative 2 plus c. Or we can rewrite this as negative 2 over x squared plus c. Another, find the antiderivative of 3 over x to the power of 5 dx. So take note here, our exponent is at the bottom, so therefore we write this, so bring it up. So take note, it's the same as the integral of 3x to the power of negative 5 dx. So the same thing, plus 1 and divided by the new exponent. So this would become x to the power of negative 4 over negative 4, then plus c. Another, if we're given 4 square root of x dx, so take note here, we will always rewrite this to exponential form. So take note, square root of x is the same as x to the power of 1/2. So take note, getting its integral or antiderivative, we will simply add 1. So 1/2 plus 1 would become 3/2. So divided by 3/2, then plus c. So getting the reciprocal of 3/2, which is 2 over 3, then times 4. So that would become 8 x to the power of 3/2 over 3 plus c. Another, what is the integral of x squared plus 1 over x squared dx? So take note, we can rewrite this x squared over x squared, that's basically 1. And we can rewrite 1 over x squared as x to the power of negative 2 dx. So take note, the integral of 1 is x. So negative 2 plus 1, so that would become negative 1 over negative 1. So simplifying further, so this would become x minus 1 over x plus c, or that would become minus x to the negative 1 plus c. Okay. Now, let's have this. Integrals are antiderivatives involving exponential and logarithmic functions. So, take note of this. The integral of a and x dx, so just copy the given, divided by natural log of the base plus c. The integral of e to the power of x dx is basically ex, then plus c. Now, another is the integral of x to the negative 1 dx, or basically this is 1 over x. That is the natural log of x plus c. So let's have an example. What is the integral of 5x dx? So with this, copy the given 5x over natural log of the base, which is 5 plus c. That's the final answer. Okay, another example. If we're given the integral of 3x plus 1 dx. So take note, we can rewrite this as 3 to the power of x times 3 to the power of 1 dx. So we can rewrite this as 3. So factor out 3 because it's a constant. Then 3x dx. So with this, copy 3. So 3 to the power of x over ln of 3 plus c. That's your final answer. Okay, another example. What is the integral of 2ex dx? So with this, just copy the given 2ex plus c. Another example. What is the integral of e to the power of x plus 2 to the power of x dx? So it's a combination of number 1 and number 2. So rewriting this is the integral of e to the power of x dx plus the integral of 2 to the power of x dx. So simplifying, this is e to the power of x plus 2 to the power of x ln of 2 plus c. Okay, another. What is the integral of 1 over x dx? So answer to this would be, or we can rewrite this as x to the power of negative 1 dx, or we can have this as ln of x plus c. Okay, another. What is the integral of 2 over x dx? So take note, we can rewrite this as 2x to the power of negative 1 dx. So with this, our integral would be 2 ln of x plus c. Okay, these are integrals or antiderivatives involving trigonometric functions. So there are 6 of these. So number 1, that's the integral of cosine x dx is sine x plus c, until number 6, which is the integral of cosecant squared x dx is negative cotangent x plus c. So take note of these. So let's have an example. What is the integral of cosine x minus sine x dx? So take note, the integral of cosine x is sine x plus c, then minus The integral of sine x is negative cosine x, then of course plus c. So since you can simplify this, so final answer is sine x plus cosine x plus c. Another example. What is the integral of sine x over cosine squared x dx? So take note, we can rewrite this as sine x over cosine x times 1 over cosine x dx. So take note, sine x over cosine x by quotient identity is tangent x, and 1 over cosine x by reciprocal identity is secant x dx. So take note for number 5, the integral of tangent x secant x dx is basically secant x plus c. Okay, another example. What is the integral of cotangent squared x dx? So take note, we can rewrite this as the integral of cosecant squared x minus 1 dx. So take note, this 2 here, it's Pythagorean identity. So we can rewrite this as the integral of cosecant squared x dx minus the integral of 1 dx. So take note for number 6, the integral of cosecant squared x dx is negative cotangent x, then the integral of 1 dx, so that would be minus x plus c. So take note as to how it is done. Okay, let's have this techniques of antidifferentiation. So let's start with the substitution rule. So take note, the integration by substitution, it is an integral that contains some functions and its derivatives. So the integral of the function g of x times, so take note, g prime of x is basically the derivative of g of x. So we can make use of the function u du. So we substitute the function by u and tu. Derivative as tu. So let's have an example. What is the integral of quantity x plus 4 to the power of 5 dx? So take note with this, we can have the substitution as u is equal to the base, which is x plus 4. Now take note, the derivative of u is du and the derivative of x is basically 1 dx. So substituting, so the integral of, instead of x plus 4, we will rewrite that as u, and to the power of 5, we will replace dx as du. So take note, plus 1 divided by the new exponent, so this would become u6 over 6 plus c. So substituting, so our u here would be x plus 4 to the power of 6 over 6 plus c. Another example. The integral of 2x minus 3 to the power of 6 dx. So again, by substitution, so let u be equal to 2x minus 3. So derivative of u is du. Derivative of 2x, that would be 2 dx. So derivative of negative 3 is 0. So since we only have dx here, so divide both sides by 2. So dx then would become du over 2. So take note, substitute. So the integral of, replace 2x minus 3 by u, then to the power of 6, then dx will be replaced with du over 2, or that's 1/2 du. So 1/2, so write it before the integral, and we can have u to the power of 7 over 7 plus c. So replace u with the given here, so that would become 2x minus 3 to the power of 7 over 2 times 7 is 14 plus c. Another example. Find the integral of quantity x to the power of 5 plus 2 to the power of 9 times 5x to the power of 4 dx. So by substitution, let u be equal to x to the power of 5 plus 2. Take note, derivative of u is du. Derivative of x to the power of 5, that's 5x to the power of 4. Derivative of constant is 0, then dx. So substituting the original given, so this would become the integral of, instead of x to the power of 5 plus 2, we'll replace that with u to the power of 9, and 5x4 dx is du. So by integral, or antiderivative, so plus 1, so this would become u to the power of 10 over 10 plus c. Now replacing u with the given, So this would become quantity x to the power of 5 plus 2 to the power of 10 over 10 plus c. Another example. Find the integral of z squared over the square root of 1 plus z cubed dz. So by substitution, let u be equal to 1 plus z cubed. Take note, derivative of u is du, derivative of 1 is 0, derivative of z cubed, that's 3z squared dz. So since we only have z squared dz here, divide both sides by 3, so z squared dz would become du over 3. So take note, rewriting this is just the same with the integral of 1 over the square root of 1 plus z cubed times z squared dz. So substituting this one, so this would become 1 over the square root of u times, so take note, z squared dz is du over 3, or that's 1/3 du. So we can replace or rewrite this as 1/3 the integral of, take note, 1 over u, square root of u is the same as u to the power of negative 1/2 du. So by integration, so negative 1/2 plus 1, that would become 1/2 over 1/2 plus c. Or getting the reciprocal of this, the inverse of 1/2 is 2. So this would become 2/3 u to the power of 1/2 plus c. Replacing u with 1 plus z cubed, so final answer here would be 2 over 3. Quantity 1 plus z cubed to the power of 1/2 plus c. Okay, another example. Find the integral of x over the square root of x squared minus 1 dx. So take note, let u here be x squared minus 1. Derivative of u is du. Derivative of x squared, that's 2x dx. So since we only have x here, so divide both sides by 2. So this would become du over 2x dx. So replacing the original equation, or rewriting this as the integral of 1 over the square root of x squared minus 1 x dx. So by substituting, this would become the integral of 1 over the square root of u times, our x dx here would be 1/2 du. So we can rewrite as 1/2 the integral of u to the power of negative 1/2 du. So negative 1/2 plus 1/2, so that would become 1/2 over 1/2. Reciprocal of 1 over 2 is 2. So our final answer would be u to the power of 1/2 plus c. Replacing u here with x squared minus 1. So final answer is quantity x squared minus 1 to the power of 1/2 plus c. Okay, another. Find the integral of dx over x cube root of ln of x. So by substitution, so let u be equal to ln of x. So derivative of u is u. Take note, derivative of ln of x, that's 1 over x dx. So with this, we can rewrite this as the integral of 1 over x cube root of ln of x dx. Or this would become 1 over, so take note here, cube root of ln of x, so ln of x, so that would be cube root of u. So take note, dx over x, that's basically du. So rewriting this, so this would be the integral of u to the power of negative 1/3 du. So getting its integral or antiderivative, so negative 1/3 plus 1, so that would become 2/3 over 2/3 plus c. Get the inverse of the denominator, so this would become 3 over 2 u to the power 2/3 plus c. Replace u with ln of x, so final answer is 3 ln of x to the power of 2/3 over 2 plus c. Let's have this integration using substitution rule and table of integrals. Now take note, these are the summary, or basically the table of integrals. Okay, so let's have this. Evaluate the following. So what's the integral of e to the power of 3 3x dx. So still by substitution, so let's have u here as 3x. So derivative of u is du, derivative of 3x is 3 dx. So with this, since we only have dx, so divide both sides by 3. So dx here would be du over 3. Now, rewriting this, so this would be the integral of e to the power of u. Then our dx is 1/3 du, or this would become 1/3. The integral of eu is just eu plus c. Substituting, our final answer would be e to the power of 3x over 3 plus c. Another, the integral of 2 to the power of 4x dx. So let u be equal to 4x. Derivative of u is du. Derivative of 4x is 4 dx. So since we only have dx, divide the entire equation by 4. So dx here would be du over 4. Rewriting this, this would become the integral of 2 to the power of u 1/4 du. Or the integral of 2 to the power of u, so that would be copy 2 to the power of u over ln of 2 plus c. And of course, we have here our constant 1/4. So final answer would be 2 to the power of 4x over 4 ln of 2 plus c. Another. So in here, let's have u here as 2x minus 1. Derivative of u is du. Derivative of 2x is 2 dx. So divide the entire equation by 2. So dx here would be du over 2. Now, rewriting this, so this is the integral of 1 over u du over 2. Or we can have that as 1/2. So the integral of 1 over u is ln of u plus c. So final answer here would be ln of, we have here 2x minus 1 over 2 plus c. Another. Evaluate the following integral. So there are 4 of these. So let's start with number 1. So cosine 4x plus 3 dx. So let u here be 4x plus 3. So derivative of u is du. Derivative of 4x is 4 dx. So divide by 4. So du over 4 is basically dx. So let's replace. So this would become the integral of cosine u, then du over 4. Or that would become 1/4. The integral of cosine u is sine u plus c. So replace u with 4x plus 3. So this is the final answer. Another. For this one, so let u be sine x. So du here, the integral derivative of sine x is cosine x dx. So rewriting, so this would become the integral of sine x is u, cosine x dx is du. So integrating this one, so this would become u squared over 2 plus c. Substituting, this would become sine. So this, since this is squared, so sine squared x over 2 plus c. That's the final answer for number 2. Number 3. So in here, let u here be sine x. The derivative of u is du. Derivative of sine x is cosine x dx. So substituting, so this will become the integral of e to the power of u and du. So since the integral of e to the power of u is just e to the power of u plus c, replace u here. So e to the power of sine x plus c. Okay, last. This one, the integral of x squared cosine quantity 6x cubed dx. So let u here be equal to 6x to the power of 3. Derivative of u is du. Derivative of 6x to the power of 3. So that would become 18x squared dx. So divide the entire equation by 18. So x squared dx would be du over 18. So rewriting this, so this would become the integral of cosine u. So x squared dx, so take note, that will be replaced with du over 18. Or that would be 1 over 18. The integral of cosine u is sine u plus c. So replace u here. So that would become sine 6x to the power of 3 over 18 plus c. Antidifferentiation to differential equations. Now, imagine you are behind a microscope in a laboratory and you're trying to count the growing number of bacteria in a petri dish. You observe that at any point in time, 1/4 of the population is reproduced. You may eventually give up counting because the bacteria are multiplying very fast, but you can use your calculus skills to find the population of bacteria at any given time. Let y denote the population at any time t, and according to your observation, the change in the population at any time is 1/4 y. Since the derivative quantifies change, the above observation can be expressed mathematically as dy over dt is equal to 1/4 y. Now take note, this is an example of a differential equation, and our objective is to recover the population y from the above equation using integration. Okay, so when you say differential equation, it contains x, y, and derivatives of y. So these are just some of the examples of differential equation. So solving differential equations means finding all possible solutions to the given differential equation. So a differential equation is a separable equation and can be expressed as f of x dx is equal to g of y dy. So with this, the integral of f of x dx is equal to the integral of gy dy. So let's have an example. Find the general solution of the following differential equation. So with this, let's cross multiply. So this would become dy is equal to 5x squared plus 3x minus 4 dx. Get the integral to both sides. The integral of dy is y. The integral of 5x squared is 5x cubed over 3. 3x is 3x squared over 2. Then minus 4x plus c. Okay, another example. Find the integral of, or the general solution of 4x plus cosine 3x. So cross multiply. So this would become dy 4x plus cosine 3x dx. Get the integral to both sides. So the integral of dy is y. The integral of 4x is 4x squared over 2. The integral of cosine 3x, so that would become 1/3 sine 3x plus c. Or simplifying, 4x squared over 2, that's 2x squared plus 1/3 sine 3x plus c. Okay, this one. What is the integral of dy dt is equal to 1/4 y. So, cross multiplying this one. So, this would become dy over y is equal to 1/4 dt. So, getting the integral to both sides. So, take note, the integral of dy over y. So, that's ln of y. And the integral of 1/4 dt. So, that would be 1/4 t plus c. Now, take note, ln of y, we can rewrite this as y is equal to e to the power of 1/4 t plus c. Or we can rewrite this as y is equal to e to the power of 1/4 t times e to the power of c. So let's have e to the power of c as a. So take note, e to the power of c, so that's a constant. So let's replace that as a. So where a is any real number, so we can rewrite this as y is equal to a times e to the power of 1/4 t. So let's have this. Now find the particular solution of the following differential equation. So dy over dx is equal to 3x squared plus 2x plus 1, given that y of 0 is 5. So again, rewriting this, so we'll get this, getting the integral to both sides. So integral of dy is y. So 3x cubed plus 2x squared over 2 plus x plus c. Or simplifying, this would become y is equal to x cubed plus x squared plus x plus c. Now take note, when you say particular solution, we will really find the value of c. So since we are given here y of 0 is equal to 5, so that would mean y is 5 when x is 0. So let's substitute. So 5, so 0 cubed plus 0 squared plus 0 plus c. So our c here is 5. So therefore, our final answer would be y is equal to x cubed plus x squared plus x plus 5. Okay, another example. dy over dx, 4x squared minus 12x. X is 3 when the y is 5, or y is 5 when x is 3. So again, rewriting, we'll get this, get the derivative to both sides, or the integral to both sides. The integral of dy is y. The integral of this is 4x cubed over 3 minus 12x squared over 2 plus c. Simplifying, 4x cubed over 3 minus 6x squared plus c. So substituting, our x here is 3 and our y is 5. So simplifying this one, the value for c here is 23. Thus, the final particular solution of this would be y is equal to 4x cubed over 3 minus 6x squared plus 20. Exponential growth or decay, bounded growth, and logistic growth. Now, for population, it can be represented with the change in y with respect to time is equal to the birth rate minus the death rate. So take note, since birth minus death rate is any real number, so we can represent that as k. So we have this. So simplifying, cross multiply, so this would become dy over y is equal to k dt. So getting the integral to both sides, so the integral of dy over y is ln of y. The integral of k dt, so take note k here is a constant, so that would become kt plus c. Now, rewriting this would become y is equal to e to the power of kt times e to the power of c. So, let's represent e to the power of c since it's a constant. So, let's rewrite it as c. So, with this, we can have our equation as y is equal to e to the power of kt times c. Now, at this point, let's improve this equation by finding the particular value of c using a particular time. So, take note here, when the time is 0, our y here would be y of 0. So, or it's the initial value. So, substituting, so this would become y of 0 is equal to e to the power of k times 0, since it's our time, times c. So, e to the power of 0, that's 1. So, therefore, our c here is equivalent to y of 0. Now, again, substituting and making use of this original equation. So, we will have there y, and take note, our c is equivalent to y of 0 times e to the power of kt. So, take note of these variables. Our y of 0 here is our initial amount when the time is 0. Our k here represent the constant it's the constant that represents the growth rate, and t here is time. So, take note, if you're given 8 to the power of k is 2 to the power of 1 over 5, it means the population doubles after 5 days. E to the power of k is equal to 3 to the power of 1/4, it means the population triples after 4 days. So, let's have an example. Suppose that a colony of lice grows exponentially. After day 1, 50 lice are counted. After 3 days, 200 were counted. How many were there originally? And what is the exponential growth equation for the colony? So take note, with our equation, y is equal to y of 0 times e to the power of kt. So take note of the given. We have here 50, so that's for day 1. Y over 1. We have 200, so that is for y3. So, we don't know what's the starting number of lice, and we also don't know its rate. So, again, making use of the original equation, so let's replace this. Our y sub 1 here at 50, so y of 0 times e to the power of k, 1. Then the other one, it's 200, is equal to y of 0 times e to the power of k, 3. So, with this, So 50 is equal to y of 0 is equal to e to the power of k. So dividing both sides by e to the power of k. So our y of 0 here would be 50 over e to the power of k. So, or we can have 50 e to the power of negative k is the initial value for y. So solve for e to the power of k. So making use of the second equation, so we have here 200. Let's replace y of 0 as 50 e to the negative k times e to the power of k times 3. So with this would become 250. So e to the power of negative k times e to the power of 3k. So multiply the same base, so you add the exponent. So 3k minus k, that would be 2k. So dividing both sides by 50, so this would become 4 is equal to e to the power of 2k. So since we are only solving for k, so let's raise this to 1/2, or we can rewrite this as ek to the power of 2. So we can also have this as 2 to the power of 2. Since our exponent here are equal, so e to the power of k is equal to 2. So solve for y of 0. So 50 is equal to y of 0. So take note, our e to the power of k is equal to 2. So dividing both sides by 2, so y of 0 is 25. So with this, y of 0 is the original number of lies. So our exponential growth equation here, y is equal to 25 times our e to the power of k, that's equivalent to 2 to the power of t. Exponential decay. Now, the rate of decay of radium is said to be proportional to the amount of radium present. If the half-life of radium is 1,690 years and there are 200 grams on hand now, how much radium will be present in 845 years? Now, take note of our equation, y is equal to y of 0 times e to the power of k t. So take note, we have here y of 0, it's 200, that's the starting amount. Our time here is 1,690 years. So after 1,690 years, the value of the element would be 100 because it's half-life. So meaning get half after that number of years. So our e to the power of k, so it's unknown. So after 845 years, the value of the element is also unknown. So solve for e to the power of k. So let's substitute. So our y here is 100 is equal to 200 times e to the power of k after 1,690 years. So dividing both sides by 200, so 1/2 is equal to 1,690 k. So raise this to 1 over 1,690, so that we can cancel 1,690. So this would become, so since our exponent here are equal, so we can also cancel. So e to the power of k is equal to 1 over 2 to the power of 1 over 1,690 years. So solving for y of 845, so y is equal to 200 times 1/2 to the power of 1 over 1,690. That's the value of our e to the power of k, then to the power of t. So since our t here is 845, so 845 over 1,690 using our calculators, so we'll end up with 141.4. Okay, bounded growth. The population is limited by some resource such as food or space. This limiting quantity is termed as carrying capacity, or let's have it as L. The rate of change of y with respect to time is proportional to the difference of carrying capacity minus rate of change. So we can have this as dy, the change in y with respect to time, is k L minus y. So cross multiplying, we will get this. So divide this one by L minus y. So we'll have dy over L minus y is equal to k dt. Getting the integral to both sides. So we will have here negative ln of L minus y is equal to kt plus c. Or this would become L minus y is equal to e to the power of negative kt times e to the power of c. Now, let e to the power of c be equal to c. So, L minus y is equal to e to the power of negative kt times c. So, if the change is lesser than the carrying capacity, so we'll get this. So, L minus y is equal to L minus y. So, L minus y is equal to c times e to the power of negative kt. So, base from here. So, our y here would be L minus c times e to the power of negative kt. Take note, k here represents the constant that represents the growth rate. Our t here is time. Our L is carrying capacity. And c here is L minus y of 0. So, let's have an example. A certain Pawikan breeding site is said to be able to sustain 5,000 Pawikans. 1,000 Pawikans are brought there initially. After a year, this increased to 1,100 Pawikans. How many Pawikans will there be after 5 years? And assume that Pawikans follow the limited growth model. So, take note, our given, our limiting capacity is 5,000. Our initial number of Pawikans is 1,000. After a year, it became 1,100. So, after 5 years, there will be how many Pawikans? So, it's a known. So, solve for C. So, our C here is L minus the initial. So, limiting capacity minus the initial. So, 5,000 minus 1,000. So, that would become 4,000. So, solve for e to the power of negative ak. So, take note, our equation is y is equal to L minus c times e to the power of negative kt. So, take note, after 1 year, so that's 1,100, carrying capacity is 5,000, our c is 4,000 times e to the power of negative k, then our time is 1. So, this would become 4,000 times e to the power of negative k is equal to 5,000 minus 1,100. So, 4,000 e to the negative k is equal to 3,900. Divide both sides by 4,000. So, e to the negative k is 3,900 over 4,000. Or e to the negative k is 0.975. So, solve for y, 5. So, again, our equation is for bounded growth is y is equal to L minus c times e to the negative kt. So, substitute. Our L is 5,000. Our c is 4,000. Our e to the negative k is 0.975 to the power of t. So, since our t here is 5, so replace it with 5, making use of your calculators. So, our y here would be around 1,475.6, or approximately, there will be 1,475 Pawikans in the breeding site after 5 years. Another example. Suppose that the newly baked cupcakes are taken out of the oven, which is set at 100 degrees. Room temperature is found to be 25 degrees, and in 15 minutes, the cupcakes are found to have a temperature of 50 degrees. Determine the approximate temperature of the cupcakes after 30 minutes. So, take note here, our limiting capacity is 25 degrees, so that's the room temperature. Our starting temp is 100 degrees. After 15 minutes, it became 50 degrees. So, to find C here, so this would be limiting minus initial. So, 25 minus 100. So, that's negative 75. So, after 30 minutes, what will be the temperature of the cupcake? So, take note, our bounded growth equation. Y is equal to L minus C times e to the negative kt. So, our y here, that's 50 degrees, 25. Our c here is negative 75, so minus negative 75, so that would become 75. e to the negative k after 15 minutes. So simplifying, you transpose. So this would become 25 is equal to 75 e to the negative 15k. So e to the negative 15k is basically 25 over 75. So raise this to 1 over 5. So we can cancel. So 25 over 25 over 75 is 1/3. So we cancel 15 here. So e to the negative k is 1/3 to the power of 1 over 15. So solving for the temperature of the cupcakes after 30 minutes. So let's substitute. Our L is 25. So minus negative 75. So that's plus 75 times our e to the negative k. It's 1/3 to the power of 1 over 15. Then our time is 30 minutes. So simplifying, so this would become 30 over 15, or that would become 2. Or simplifying, the temperature of the cupcake after 30 minutes is approximately 33.33 degrees. So take note of this. Okay, let's have this logistic growth. So further studies say that it is more appropriate for the rate of change of a population to be expressed as proportional to both the size of the population, y, and the difference between a limiting quantity, L, and the size of the population. So that would mean dy over dt is equal to ky, so limiting quantity minus the size of the population y. So cross multiplying, we get this. So divide both sides by y, ly, so we get this one. So factor out 1 over L, so this would become 1 over y plus 1 over L minus y dy k dt. So getting the integral to both sides, so ln of y minus ln of L minus y is equal to L k t plus c. So this would become ln of y over L minus y, L k t plus c. So we get this, or we can rewrite this as y is equal to L minus y e to the power of L k t plus c. So take note of this. So deriving the equation for logistic growth. So we get this red equation here. So L here is carrying capacity, or that's the limiting capacity. The K is constant that represents the growth rate. T is time. And to find C, it's limiting capacity minus the starting amount over the starting amount or value. Let's have an example. 10 Philippine eagles were introduced to a national park 10 years ago. There are now 23 eagles in the park. The park can support a maximum of 100 eagles. Assuming a logistic growth model, when will the eagle reach 50? So take note, our limiting capacity is 100. The starting number of eagles is 10. So after 10 years, 23. So what will be the time so that the number of eagle population will become 50? So our C here is also unknown. So our e to the power of negative lk is also unknown. So t here, it's also unknown. So solve for c. So take note c given this equation. So our L is 100 minus 10 over 10. So the value for c here is 9. Okay, solving for e to the power of negative l k is equal to e to the power of negative 100 k. So y, so again, the logistic growth model is this equation. So let's have here 23 is equal to 100 over 1 plus our c is 9, e to the negative 100. Then after 10 years, then k. So substituting, we will get this one. So cross multiplying, we will get this. So 9 e to the negative 1000 k. So 100 divided by 23, then minus 1, we will get 3.35. So e to the negative 1000k would become 0.37, or e to the negative 100k would become 0.906. So solving for t. So again, substituting in the original equation. So we have here 100 over 1 plus 9, our e to the negative lkt. So take note, our L here is 100. That's 0.906. Then t. So take note, we have here 50. So substituting here and manipulating the equation, we get this, we cross multiply. So 100 divided by 50, we got 2. So transfer 1 to the other side. So 2 minus 1, it's 1. Then divided by 9. So that will become 19. So in here, 0.906 to the power of t is equal to 1 over 9. So we can rewrite this as the logarithm of 1 over 9 to the base of 0.906 is equal to t. So making use of your calculators, the value for our t here is approximately 22